This lecture is about probability, and I want you to know that you don't have to be able to do all the math. I want you to approach this conceptually, and I want you to understand how we use probability, the chance that things will happen in inferential statistics. So the first question to ask is why? Why do we care about probability? Well, probability is the underlying concept behind us being able to tell how confident we are that our answer or decision represents reality. We approach the world as if things happen by chance. And if we can show that something is different than it would have been by chance or with the status quo, then we can be confident that we've got an answer or something happening. Let me give you a silly example. I can do some research and I invent happy pills. And I put a lot of time and energy and effort into it. And so I'm going to go and find some manufacturer who's going to invest money in a factory and marketing and all of that and sell these happy pills to people so that they will be happy. But then when the reality hits, what if I haven't been careful enough in my research and it turns out that the happy pills make a portion of the people really, really sick? So that's why that's a silly, silly example, but we want to be able to know how confident we are in our answer. So let me give you a more realistic suppose. We've got a question. Does eating breakfast every morning change the reading scores for low socioeconomic third graders? So we know that children in poverty go hungry a lot. So our question is, if they eat breakfast, will it help them to learn better? We always start with our null hypothesis, and that is that the status quo is where we should stay. There will be no change in the reading scores after eating breakfast. Of course, our alternative hypothesis, what we're hoping will be correct, is that there will be a change in the reading scores after these kids eat breakfast. Notice that the change in my question could be positive or negative. Maybe some kids their reading's gonna become poorer after they eat breakfast. So this is kind of a silly example too, but you get the idea. So I've identified 50 low socioeconomic status third graders in my school. That's my population. And I'm gonna sample 10 of them and provide them with breakfast for 30 days. Now, I'm not really that cruel. This is totally made up. And I'm looking to see if there was a change in their reading scores after 30 days of eating these breakfasts for my sample of 10 kids. So the first thing I do is I set my alpha level. And you'll remember that that's my willingness, the probability that I can make a type 1 error and I'm still going to be happy and be able to live with it. So I'm going to set that to 5%, which means I would write it this way, alpha equals 0.05. Now let's think about what I really want to know. After I do all this, out of my 10 students in the sample, 6 of them had reading scores that changed. Are the changes the same as they would have been if I hadn't intervened with breakfast? That's what I'm really asking with my null hypothesis. I'm saying that those 6 kids would have changed whether they had breakfast or not. Any changes could just be chalked up to chance. Let's look at the underlying distribution for those 10 students. In other words, how likely is it that all 10 of them would change? So n is 10, and the probability of a change is 50-50, one way or the other. So for every student, there's a 50-50 chance they would change. That's the only possibilities there are. It's exclusive. They either change or they don't change. So this is where I go to a table of the binomial distribution, and I look for my n, 10 kids in my sample, and the chances of change are 50-50. And right there, they've already worked it out for me. I don't have to do any math. There's the chances of a change in 0 kids, 1 kid, 2 kids, 3 kids, and so on down to 10. Now, if you look really carefully at these numbers, you'll start to have a pattern jump out at you. And this is where the underlying distribution comes in. If I look carefully at those numbers and I were to graph them out, it forms a very familiar shape, doesn't it? So now I'm going to look at my students. I had 6 of them. What's the probability that 6 of them would change, either positive or negative? So I look in that table, and for the number of changes, 6, the probability of that happening is 0.21. And that's, my alpha was set at 0.05. Now look at this. My probability of 6 of them changing is much bigger than the alpha that I set. So that means there's more than a 5% chance that I would be making a type 1 error. And in this case, I keep my null hypothesis. I have to retain the null hypothesis that those 6 kids would have made a change whether they had breakfast or not. So here's your takeaways. There's an underlying distribution for probabilities across, and it looks a lot like a normal curve. We'll go into that a little bit more. If the probability of something happening is greater than your alpha, you keep the null hypothesis. If the probability is less than alpha, that's when you can reject the null hypothesis, because you're able to say, I'm really confident that this was unusual, that this was much more than would have happened by chance.